A supercell is a thunderstorm that is characterized by the presence of a mesocyclone, a deep, persistently rotating updraft. For this reason, these storms are sometimes referred to as rotating thunderstorms. Of the four classifications of thunderstorms, supercells are the overall least common and have the potential to be the most severe. Supercells are often isolated from other thunderstorms, and can dominate the local weather up to 32 kilometers away. Supercells are often put into three classification types: classic, low precipitation and high precipitation. LP supercells are usually found in climates that are more arid, such as the high plains of the United States, and HP supercells are most often found in moist climates. Supercells can occur anywhere in the world under the right pre-existing weather conditions, but they are most common in the Great Plains of the United States in an area known as Tornado Alley and in the plains of Argentina, Uruguay and southern Brazil. Characteristics: supercells are usually found isolated from other thunderstorms, although they can sometimes be embedded in a squall line. Typically, supercells are found in the warm sector of a low-pressure system propagating generally in a northeasterly direction in line with the cold front of the low-pressure system. Because they can last for hours, they are known as quasi-steady-state storms. Supercells have the capability to deviate from the mean wind. If they track to the right or left of the mean wind, they are said to be right movers, or left movers, respectively. Supercells can sometimes develop two separate updrafts with opposing rotations, which splits the storm into two supercells, one left mover and one right mover. Supercells can be any size, large or small, low or high-topped. They usually produce copious amounts of hail, torrential rainfall, strong winds, and substantial downbursts. Supercells are one of the few types of clouds that typically spawn tornadoes within the mesocyclone, although only 30% or fewer do so. Geography: supercells can occur anywhere in the world under the right weather conditions. The first storm to be identified as the supercell type was the Wokingham storm over England, which was studied by Keith Browning and Frank Ludlam in 1962. Browning did the initial work that was followed up by Lemon and Doswell to develop the modern conceptual model of the supercell. To the extent that records are available, supercells are most frequent in the Great Plains of the central United States and southern Canada extending into the southeastern U.S. and northern Mexico, east-central Argentina and adjacent regions of Uruguay, Bangladesh and parts of eastern India, South Africa, and eastern Australia. Supercells occur occasionally in many other mid-latitude regions, including eastern China and throughout Europe. The areas with highest frequencies of supercells are similar to those with the most occurrences of tornadoes. See tornado climatology and Tornado Alley. Anatomy of a supercell: the current conceptual model of a supercell was described in Severe Thunderstorm Evolution and Mesocyclone Structure as related to tornadogenesis by Leslie R. Lemon and Charles A. Doswell. 3. Supercells derive their rotation through tilting of horizontal vorticity caused by wind shear. Strong updrafts lift the air turning about a horizontal axis and cause this air to turn about a vertical axis. This forms the deep rotating updraft, the mesocyclone. A cap or capping inversion is usually required to form an updraft of sufficient strength. The cap puts an inverted layer above a normal boundary layer, and by preventing warm surface air from rising, allows one or both of the following: air below the cap warms and/or becomes more moist, air above the cap cools. This creates a warmer, moister layer below a cooler layer, which is increasingly unstable. When the cap weakens or moves, explosive development follows. In North America, supercells usually show up on Doppler radar as starting at a point or hook shape on the southwestern side, fanning out to the northeast. The heaviest precipitation is usually on the southwest side, ending abruptly short of the rain-free updraft base or main updraft. The rear flank downdraft, or RFD, carries precipitation counterclockwise around the north and northwest side of the updraft base, producing a hook echo that indicates the presence of a mesocyclone. Structure of a supercell: overshooting top. This dome feature appears above the strongest updraft location on the anvil of the storm. It is a result of a very powerful updraft. enough to break through the upper levels of the troposphere. An observer who is at ground level too close to the storm is unable to see the overshooting top due to the fact that the anvil blocks the sight of this feature. Anvil: an anvil forms when the storm's updraft collides with the upper levels of the lowest layer of the atmosphere, or the troposphere, and has nowhere else to go due to the laws of fluid dynamics, specifically pressure, humidity, and density. The anvil is very cold and virtually precipitation-free, even though virga can be seen falling from the forward-sheared anvil. Since there is so little moisture in the anvil, winds can move freely. The clouds take on their anvil shape when the rising air reaches 15,200 (21,300 meters or more. The anvil's distinguishing feature is that it juts out in front of the storm like a shelf. In some cases, it can even shear backwards, called a back-sheared anvil, another sign of a very strong updraft. Precipitation-free base: this area, typically on the southern side of the storm in North America, is relatively precipitation-free. This is located beneath the main updraft, and is the main area of inflow. While no precipitation may be visible to an observer, large hail may be falling from this area. A region of this area is called the vault. It is more accurately called the main updraft area. Wall cloud: the wall cloud forms near the downdraft-updraft interface. This interface is the area between the precipitation area and the precipitation-free base. Wall clouds form when rain-cooled air from the downdraft is pulled into the updraft. This wet, cold air quickly saturates as it is lifted by the updraft, forming a cloud that seems to descend from the precipitation-free base. Wall clouds are common and are not exclusive to supercells. Only a small percentage actually produce a tornado, but if a storm does produce a tornado, it usually exhibits wall clouds that persist for more than 10 minutes. Wall clouds that seem to move violently up or down, and violent movements of cloud fragments near the wall cloud are indications that a tornado could form. Mammatus clouds: mammatus are bulbous or pillow-like cloud formations extending from beneath the anvil of a thunderstorm. These clouds form as cold air in the anvil region of a storm sinks into warmer air beneath it. Mammatus are most apparent when they are lit from one side or below, and are therefore at their most impressive near sunset or shortly after sunrise when the sun is low in the sky. Mammatus are not exclusive to supercells and can be associated with developed thunderstorms and cumulonimbus. Forward flank downdraft: this is generally the area of heaviest and most widespread precipitation. For most supercells, the precipitation core is bounded on its leading edge by a shelf cloud that results from rain-cooled air within the precipitation core spreading outward and interacting with warmer, moist air from outside of the cell. Between the precipitation-free base and the FFD, a vaulted, or cathedral feature can be observed. In high-precipitation supercells, an area of heavy precipitation may occur beneath the main updraft area where the vault would alternately be observed with classic supercells. Rear flank downdraft: the RFD of a supercell is a very complex and not yet fully understood feature. RFD mainly occur within classic and HP supercells, although RFDs have been observed within LP supercells. The RFD of a supercell is believed to play a large part in tornadogenesis by further tightening rotation within the surface mesocyclone. RFDs are caused by mid-level steering winds of a supercell colliding with the updraft tower and moving around it in all directions. Specifically, the flow that is redirected downward is referred to as the RFD. This downward surge of relatively cool mid-level air, due to interactions between dew points, humidity, and condensation of the converging of air masses, can reach very high speeds and is known to cause widespread wind damage. The radar signature of an RFD is a hook-like structure where sinking air has brought with it precipitation. Vault: a vault is not observed with all supercells. The vault can only be identified visibly due to it visibly appearing to be free of precipitation but usually containing large hail. On Doppler radar, the region of very high precipitation echoes with a very sharp gradient perpendicular to the RFD. Flanking line: a line of smaller cumulonimbus or cumulus that form in the warm rising air pulled in by the main updraft. Due to convergence and lifting along this line, land spouts sometimes occur on the outflow boundary of this region. Radar features of a supercell. Hook echo or pendant. The hook echo is the area of confluence between the main updraft and the rear flank downdraft. This indicates the position of the mesocyclone, and probably a tornado. Bounded weak echo region. This is a region of low radar reflectivity bounded above by an area of higher radar reflectivity with an untilted updraft. This is evidence of a strong updraft, and oftentimes the presence of a tornado. Inflow notch. A notch of weak reflectivity on the inflow side of the cell. This is not a V-notch. V-notch, a V-shaped notch on the leading edge of the cell, opening away from the main downdraft. This is an indication of divergent flow around a powerful updraft. Hail spike. This three-body scatter spike is a region of weak echoes found radially behind the main reflectivity core at higher elevations when large hail is present. Supercell variations. Supercell thunderstorms are sometimes classified by meteorologists and storm spotters into three categories. However, not all supercells fit neatly into any one category, being hybrid storms, and many supercells may fall into different categories during different periods of their lifetimes. The standard definition given above is referred to as the classic supercell. All types of supercells typically produce severe weather. Low precipitation. LP supercells contain a small and relatively light precipitation core that is well separated the updraft. The updraft is intense and LPs are in flow-dominant storms. The updraft tower is typically more strongly tilted and the deviant rightward motion lesser than for other supercell types. The forward flank downdraft is noticeably weaker than for other supercell types and the rear flank downdraft is much weaker or even visually absent in many cases. Like classic supercells, LP supercells tend to form within stronger mid to upper level storm relative wind shear, however, the atmospheric environment leading to their formation is not well understood. The moisture profile of the atmosphere, particularly the depth of the elevated dry layer, also appears to be important and the low to mid-level shear may also be important. This type of supercell may be easily identifiable with sculpted cloud striations in the updraft base or even a corkscrewed, or barber pole appearance on the updraft, and sometimes an almost anorexic look compared to classic supercells. This is because they often form within drier moisture profiles leaving LPs with little available moisture despite high mid to upper level environmental winds. They most often dissipate rather than turning into classic or HP supercells, although it is still not unusual for LPs to do the latter, especially when moving into a much moister air mass. LPs were first formally described by Howard Bluestein in the early 1980s, although storm-chasing scientists noticed them throughout the 1970s. Classic supercells may wither yet maintain updraft rotation as they decay, becoming more like the LP type in a process known as downscale transition that also applies to LP storms, and this process is thought to be how many LPs dissipate. LP supercells rarely spawn tornadoes and those that form tend to be weak, small, and high-based tornadoes, but strong tornadoes have been observed. These storms, although generating lesser precipitation amounts and producing smaller precipitation cores, can generate huge hail. LPs may produce hail larger than baseballs in clear air where no rainfall is visible. LPs are thus hazardous to people and animals caught outside as well as to storm chasers and spotters. Due to the lack of a heavy precipitation core, LP supercells often exhibit relatively weak radar reflectivity without clear evidence of a hook echo, when in fact they are producing a tornado at the time. LP supercells may not even be recognized as supercells in reflectivity data unless one is trained or experienced on their radar characteristics. This is where observations by storm spotter and storm chasers may be of vital importance in addition to Doppler velocity radar data. High-based shear funnel clouds sometimes form midway between the base and the top of the storm, descending from the main CB cloud. Lightning discharges may be less frequent compared to other supercell types, but on occasion LPs are prolific sparkers, and the discharges are more likely to occur as intra-cloud lightning rather than cloud-to-ground lightning. In North America, these storms most prominently form in the semi-arid Great Plains during the spring and summer months. Moving east and southeast, They often collide with moist air masses from the Gulf of Mexico, leading to the formation of HP supercells in areas just to the west of Interstate 35 before dissipating at variable distances farther east. LP supercells have been observed as far east as Illinois and Indiana, however. LP supercells can occur as far north as Montana, North Dakota, and even in the prairie provinces of Alberta, Saskatchewan, and Manitoba in Canada. They have also been observed by storm chasers in Australia and Argentina. LP supercells are quite sought after by storm chasers, because the limited amount of precipitation makes sighting tornadoes at a safe distance much less difficult than with a classic or HP supercell, and more so because of the unobscured storm structure unveiled. During spring and early summer, areas in which LP supercells are readily spotted include southwestern Oklahoma and northwestern Texas, among other parts of the western Great Plains. High precipitation. The HP supercell, or hypercell thunderstorm, has a much heavier precipitation core that can wrap all the way around the mesocyclone. These are especially dangerous storms, since the mesocyclone is wrapped with rain and can hide a tornado from view. These storms also cause flooding due to heavy rain, damaging downbursts and weak tornadoes, although they are also known to produce strong to violent tornadoes. They have a lower potential for damaging hail than classic and LP supercells, although damaging hail is possible. It has been observed by some spotters that they tend to produce more cloud-to-ground and intra-cloud lightning than the other types. Also, unlike the LP and classic types, severe events usually occur at the front of the storm. The HP supercell is the most common type of supercell in the United States east of Interstate 35, in the southern parts of the provinces of Ontario and Quebec in Canada, and in the central portions of Argentina and Uruguay. Mini supercell or low-topped supercell, whereas classic, HP, and LP refer to different precipitation regimes and mesoscale frontal structures. Another variation was identified in the early 1990s by John Davis. These smaller storms were initially called mini supercells but are now commonly referred to as low-topped supercells. These are also subdivided into classic, HP and LP types. Effects. Supercells can produce large hail, damaging winds, deadly tornadoes, flooding, dangerous cloud-to-ground lightning, and heavy rain. Severe events associated with a supercell almost always occur in the area of the updraft-downdraft interface. In the Northern Hemisphere, this is most often the rear flank of the precipitation area in LP and classic supercells, but sometimes the leading edge of HP supercells. While tornadoes are perhaps the most dramatic of these severe events, all are dangerous. High winds caused by powerful outflow can reach over 148 km/h and downbursts can cause tornado-like damage. Flooding is the leading cause of death associated with severe weather. Note that none of these severe events are exclusive to supercells, although these events are highly predictable once a supercell has formed. Examples: the supercell is a global phenomenon, as evidenced by these examples. Asia. Some reports suggest that the deluge on July 26, 2005 in Mumbai, India was caused by a supercell when there was a cloud formation 15 kilometers high over the city. On this day 944 mm of rain fell over the city, of which 700 mm fell in just 4 hours. The rainfall coincided with a high tide, which exacerbated conditions. Australia. On April 14, 1999, a severe storm later classified as a supercell hit the east coast of New South Wales. It is estimated that the storm dropped 500,000 tons worth of hailstones during its course. At the time it was the most costly disaster in Australia's insurance history, causing an approximated $2.3 billion Australian dollars worth of damage, of which $1.7 billion Australian dollars was covered by insurance. On February 27, 2007 a supercell hit Canberra, dumping nearly 39 centimetres of ice and civic. The ice was so heavy that a newly built shopping centre's roof collapsed, birds were killed and the hail produced from the supercell, and people were stranded. The following day many homes in Canberra were subjected to flash flooding, caused either by stormwater infrastructure's inability to cope or through mudslides from cleared land. In 2010, on March 6, supercell storms hit Melbourne. The storms caused flash flooding in the centre of the city and tennis ball-sized hailstones hit cars and buildings, causing more than $220 million worth of damage, and sparking 40,000-plus insurance claims. In just 18 minutes, 19 cm of rain fell, causing havoc as streets were flooded and trains, planes and cars were brought to a standstill. That same month, on March 22, 2010, a supercell hit Perth. This storm was one of the worst in the city's history, causing hailstones of 6 centimeters in size and torrential rain. The city had its average March rainfall in just 7 minutes during the storm. Hailstones caused severe property damage, from dented cars to smashed windows. The storm itself caused more than $100 million in damage. South America, an area in South America known as the Tornado Corridor, is considered to be the second most frequent location for severe weather, after Tornado Alley in the United States. The region, which covers portions of Argentina, Uruguay, Paraguay and Brazil during the spring and summer, often experiences strong thunderstorm, which may include tornadoes. One of the first known South American supercell thunderstorms to include tornadoes occurred on September 16, and destroyed the town of Rojas. In September 20, 1926, an EF4 tornado struck the city of Encarnacia-Cuben, killing over 300 people, making it the second deadliest tornado in South America. On April 21, 1970, the town of Fray Marcos in the Department of Florida, Uruguay experienced an F4 tornado that killed 11, the strongest in the history of the nation. January 10, 1973 saw the most severe tornado in the history of South America. The San Justo tornado, 105 km north of the city of Santa Fe, was rated EF5, making it the strongest tornado ever recorded in the Southern Hemisphere, with winds exceeding 400 km/h. On April 13, 1993, in less than 24 hours in the province of Buenos Aires was given the largest tornado outbreak in the history of South America. There were more than 300 tornadoes recorded, with intensities between F1 and F3. The most affected towns were Henderson, Udempilita and Mar del Plata. In December 2000, a series of 12 tornadoes affected the greater Buenos Aires and the province of Buenos Aires, causing serious damage. One of them struck the town of Guernica, and just 2 weeks later, in January 2001, an EF3 again devastated Guernica, killing 2 people. The December 26, 2003 tornado F3 happened in Córdoba, with winds exceeding 300 km/h, which hit Cúcuta capital, hit just 6 km from the city center, in the area known as CPC Route 20, especially neighborhoods of San Roque and Villa Fabric, killing 5 people and injuring hundreds. In 2004, the tornado that destroyed the state of São Paulo was one of the most destructive in the state. Destroyed several industrial buildings, with 400 houses, left 1 dead and 11 wounded. The tornado was rated EF3, but many claim it was a tornado EF4. In November 2009, 4 tornadoes category F1 and F2 reached the town of Posadas, Argentina, generating serious damage in the city. 3 of the tornado-affected area of the airport, causing damage in Barrio Bila copyright N. On April 4, 2012, the Grand Buenos Aires was hit by the storm Buenos Aires, with intensities F1 and F2, which left nearly 30 dead in various locations. The February 21, 2014, in Berazategui, tornado intensity F1 caused material damage including a car was, with 2 occupants inside, which was elevated a few feet off the ground and flipped over asphalt. Both the driver and his passenger were slightly injured. The tornado caused no fatalities. The severe weather that occurred on Tuesday, August 11 had features rarely seen in such magnitude in Argentina. In many towns of La Pampa, San Luis, Buenos Aires and Córdoba, intense hailstones fell up to 6 cm in diameter. All day Sunday, December 8, 2013 was recorded severe storms in the center and the coast. The most affected province was Cúcuta, Storms and supercells type bioechoes also developed in Santa Fe and San Luis. Europe. In 2009, on the night of Monday, May 25, a supercell formed over Belgium. It was described by Belgian meteorologist Frank de Bouzet as one of the worst storms in recent years, and caused much damage in Belgium, mainly in the provinces of East Flanders, Flemish Brabant and Antwerp. The storm occurred between about 1 a.m. and 4 a.m. local time. An incredible 30,000 lightning flashes were recorded in 2 hours, including 10,000 cloud-to-ground strikes. Hailstones up to 6 centimeters across were observed in some places and wind gusts over 90 km/h. In Meln near Ghent a gust of 101 km/h was reported. Trees were uprooted and blown onto several motorways. In Lille a loaded goods train was blown from the rail tracks. On August 18, 2011, the rock festival Pukkelpop in Kaluit, Hasselt may have been seized by a supercell with mesocyclone around 1815. Tornado-like winds were reported, trees of over 30 centimeters diameter were felled and tents came down. Severe hail scourged the campus. 5 people reportedly died and over 140 people were injured. 1 more died a week later. The event was suspended. Buses and trains were mobilized to bring people home. On June 28, 2012, 3 supercells affected the Midlands of England. One of them produced hailstones reported to be larger than golf balls, with conglomerate stones up to 10 cms across. Burbage in Leicestershire saw some of the most severe hail. Another supercell produced a tornado near Slefford, in Lincolnshire. Severe thunderstorms also affected the northeast region of England. One such storm struck the Tyneside area without warning at the height of the evening rush hour, causing widespread damage and travel chaos, with people abandoning cars and being trapped due to lack of public transport. Flooded shopping malls were evacuated, Newcastle Central Station was shut, as was the Tyne and Wear Metro, and main road routes were flooded, leading to massive tailbacks. 999 landline services were knocked out in some areas and the damage ran to huge amounts only visible the next day after water cleared. Many parts of County Durham and Northumberland were also affected, with thousands of homes across the northeast left without power due to lightning strikes. Lightning was seen to hit the Tyne Bridge. In Europe, the mini supercell, or low-topped supercell, is very common, especially when showers and thunderstorms develop in cooler polar air masses with a strong jet stream above, especially in the left exit region of a jet streak. North America, the Tornado Alley is a region of the central United States where severe weather is common, particularly tornadoes. Supercell thunderstorms can affect this region at any time of the year, but they are most common in the spring. Tornado watches and warnings are frequently necessary in the spring and summer. Most places from the Great Plains to the east coast of the United States and north as far as the Canadian Prairies, the Great Lakes region, and the St. Lawrence River will experience one or more supercells each year. Gainesville, Georgia was the site of the 5th deadliest tornado in U.S. history in 1936, where Gainesville was devastated and 203 people were killed. The 1980 Grand Island tornado outbreak affected the city of Grand Island, Nebraska on June 3, 1980. 7 tornadoes touched down in or near the city that night, killing 5 and injuring 200. The Elie, Manitoba tornado was an F5 that struck the town of Elie, Manitoba on June 22, 2007. While several houses were leveled, no one was injured or killed by the tornado. A massive tornado outbreak on May 3, 1999 spawned an F5 tornado in the area of Oklahoma City, Oklahoma that had the highest recorded winds on Earth. This outbreak spawned over 66 tornadoes in Oklahoma alone. On this day throughout the area of Oklahoma, Kansas and Texas, over 141 tornadoes were produced. This outbreak resulted in 50 fatalities and 895 injuries. A series of tornadoes, which occurred in May 2013, caused severe devastation to Oklahoma City in general. The first tornado outbreaks occurred on May 18 to May 21 when a series of tornadoes hit. One of the storms formed an EF5 tornado, also known as the Moore tornado, which traveled across Oklahoma City, causing a severe amount of disruption. This tornado was first spotted in Newcastle. It touched the ground for 39 minutes, crossing through a heavily populated section of Moore. Winds with this tornado peaked at 210 miles per hour. 23 fatalities and 377 injuries were caused by the tornado. 61 other tornadoes were confirmed during the storm period. Later on in the same month, on the night of May 31, 2013, another 9 deaths were confirmed from a series of tornadoes and funnel clouds which hit nearby areas. South Africa. South Africa witnesses several supercell thunderstorms each year with the inclusion of isolated tornadoes. On most occasions these tornadoes occur in open farmlands and rarely cause damage to property, as such many of the tornadoes which do occur in South Africa are not reported. The majority of supercells develop in the central, northern, and northeastern parts of the country. The Free State, Gauteng, and KwaZulu-Natal are typically the provinces where these storms are most commonly experienced, though supercell activity is most certainly not limited to these provinces. On occasion, hail reaches sizes in excess of golf balls, and tornadoes, though rare, also occur. On the 6th May 2009 a well-defined hook echo was noticed on local South African radars, along with satellite imagery that supported the presence of a strong supercell storm. Reports from the area indicated heavy rains, winds and large hail. On Sunday, October 2, 2011, 2 devastating tornadoes tore through 2 separate parts of South Africa on the same day, hours apart from each other. The first, classified as an EF2 hit McKellen, the informal settlement outside Vicksburg, Free State, which devastated shacks and homes, uprooted trees, and killed 1 small child. The second, which hit the informal settlement of Duduza, Nigel in the Gauteng province, also classified as EF2 hit hours apart from the one that struck Vicksburg. This tornado completely devastated parts of the informal settlement and killed 2 children, destroying shacks and RDP homes. Gallery. See also, convective storm detection, pseudo-cold front, pseudo-warm front, references. External links. Structure and dynamics of supercell thunderstorms, Lemon, Leslie R. on the mesocyclone dry intrusion, and tornadogenesis, Electronic Journal of Severe Storms Meteorology.